So today we're going to be looking at this question, and then we're going to be working it out, and it's going to be a pretty long video, so I'm sorry about that. So let's just read this question and then jump right into it. So the diagram shows a rectangle inscribed in an ellipse. The ellipse is made by placing thumbtacks at the end at the points -4, 0, and 4, 0. The ends of the piece of the string are attached to the tacks, one end at each tack. A pencil is placed in the loop formed by the string. As the string is kept tight, the pencil traces the two branches of the ellipse, one above the x-axis and one below. The length of the string connecting the two tacks are 10 units. Use your knowledge of analytic geometry and calculus to create the response in which you 1. Use the properties of the ellipse to determine the standard form of the equation representing the ellipse. 2. Find a function a of x that models the area of the inscribed rectangle. And 3. Use the principles of calculus to find the dimensions and the inscribed rectangle of the maximum area. Be sure to show your work. So I already went ahead and did the graphs that we're going to be using today. And so the first part of the question, they're asking you about the ellipse. So we need to form the equation of the ellipse, which looks like this, which is x squared over a squared plus y squared over b squared is equal to 1. That is the standard equation for an ellipse. So we're going to have to find a and we're going to have to find b. Well, this part we're going to be finding a. So how we're going to find a is we know that the ellipse is centered at the origin, which is 0, 0. So we're not going to have to move it anywhere, and it's not going to be any different. And then we also know that there is unit of 10, which is the distance or the length of the ellipse. And then the inside of the rectangle is 4 or 8 units long. So we're missing 2 units. There's 1 unit here and 1 unit on the other side, making half of the distance 5. So our a is going to be 5 and -5. So now that we have our a, our b, we're going to have to look at a different graph. Our b, we're actually going to be using the Pythagorean theorem, which is, what is the Pythagorean theorem? A squared plus b squared equals c squared. So this is the graph that I made. It's supposed to look like the rectangle inside of the ellipse, but it's kind of messed up. So this is the top of it, and then these are the sides, which come to 4, and then this is the part where it's outside. Okay, so a we know it's going to be 4 because it's the distance between the center to the out part of it. So we need to know what b is, so we don't know what it is, but we do know what c is, because c is the length or the distance. And because we know this part right here, we also know this part, which is 5. So we know a and we know c, so let's plug it in and find out what b is. So a is 4 squared plus, and then carry the b down, is equal to c, which is 5 squared. So we're going to do the squares. 16 plus b squared equals 25. Now we want b by itself, so we have b squared. And how to do b by itself? We move the 16 over, and we get 9. So now we need to get b directly by itself. So we need to get rid of this exponent, and how we do that is doing the opposite of that, which is the square root. So b is going to be 9 square root, so that would be 3. Now we know what our b is, and we also know what our a is. We can fill in our a and b in the equation. So x squared over a, which is 5, plus y squared over our b, which is 3, don't forget the squares like I just did, is equal to 1. So then we need to do our squares. X squared over 25 plus y squared over 9 is equal to 1. That is the answer 2. It's kind of hard to see. There we go. Well, okay. So, question number 2 is asking about the area of the shaded region, which is a of x, which is, they want the area of the shaded okay. So, how we're going to do that is okay, so we're going to look at this graph that we have here, or that I made here. This is just one part of it, because we're just needing to look at one part. If we can break it apart, then it's going to be a lot simpler for us. If we had to deal with the whole thing, it's going to be difficult. So since we're breaking it apart, we actually need to put a 4 in front of the shaded region. So then we are just looking at this one part. So now we need to figure out what our x and our y is. So we need to figure out this length and this length, which our equation is going to look like that. But we need to figure out what those two are. So we just did our equation for the ellipse, and can we not just solve for y in that equation? Y squared over 9 equals 1. Okay, so this is our equation. Let's solve for y in this equation. So we need to get y by itself. So how do we get y by itself? We move this part to the other side. So then we have y squared over 9 equals 1 minus x squared over 25. Now, let's give this a little bit more leeway. Okay. Now we want to move this 9. So we want to do the opposite, because we're dividing, so we want to do the opposite. So we're going to multiply by 9. And if we do it to one side, we have to do it to the other side. So then we have y squared is equal to 9 times 1 minus x squared over 25. All that's left now is the square root. And what did we do earlier? We did square root of that. 9 times 1 minus x squared over 25. And yes, you can reduce that to 3 square root of 1 minus all of that. So then we have our y. So now that we have our y, we can actually place this y in the original equation we came up with the second part. So our a of x equals 4x of y. So let's put this y in for our y here. So it's going to be equal to 4x. And then our y, which is times 3 square root of 1 minus x squared over 25. And we're going to get 12x square root of 1 minus x over 25. And that is going to be our area so that is our answer for part 2, right there. Next part is to find the max area of the inscribed angle. You will have to take the derivative of a of x to find the max area, which is going to be a lot of work, I'm not going to lie. So part 3, we want to take the derivative. Let me write this down here before I start talking again. One minus x squared over 25. Okay. So we gotta take the derivative of this part, and how we do derivatives is a fun way. So there's a lot to deal with in this equation, so we're gonna break it apart. And we have d over dx is equal, well, not equal, times all of this. And we're doing it step by step. I just messed that up. We're going to do it step by step. And so we're going to deal with this part inside first. So we're going to put this as 25 over 25. Don't forget your negative sign in there. Okay. And so then we have 25, the square root of 25, which is actually 5. So we can actually take that out. So then we're only left with 25 minus x squared all over 5. And then we're going to our next step, which we can take the 12 and the 5 out. So outside of the derivative. So you have 12 over 5 dx. Then whatever is left, 25 minus x squared. Now, with that, we are actually going to have to break it apart even more and do the chain rule, which is even lovelier. So the chain rule is going to make it look like 12 over 5, because that's just constant now, d over dx. Now we're going to break it apart. So we have to do the first part times the derivative of the second part. Plus the second part times the derivative of the first part. And now we gotta do all of that work, and we would still have to bring that constant down. Don't forget your d of dx. So the derivative of this, we're going to come out of as 1 over 2 square root of the same thing. Times the derivative of the inside, because we can't just do it once. And then plus, let me scoot this over, 25 minus x squared, and that's the inside of that. Now we're going to put everything together. 12 over 5, d over dx, and we're going to combine everything that we can combine. So we have 2x squared over 2 square root of 25 minus, sorry, push the button on my pen, squared plus square root of 25 minus x squared. Almost done now. So then we have the 2 and the 2, which we can cancel out. Now we're just doing the basic maneuvers of simplifying. So then we're almost done. Now we're going to take it out of the derivative. And we're going to be left with negative x squared plus 25 minus x squared over square root of 25 minus x squared. We're always going to have to do that. Then we can simplify it even more. Oh, 2x squared over that. One more. We'll have now, because it's a fraction times a fraction, we can actually put everything together now. And we're almost done with this part. 24x squared over 5, because of the 5, and then times the bottom. 25 minus x squared. So that is our derivative of that. Now we got to find the critical points by using this equation right here that we got from there. So how we're going to do that is set it equal to 0. So we're going to take this equation here. This is just one part of part 3. We got to do the other parts now. Alright, so set it equal to 0. So we're going to take 300 minus 24 x squared is equal to 0. We want x by itself. So to get x by itself, we have to move the 300 over. So we have negative 24 x squared equals negative 300. Then we're going to divide by 24. Divide by 24, have x squared is equal to 25 over 2. Okay. Now we have the power up here. So we want to do how we've been doing, square root of them. So then we're going to have plus or minus square root of 25 over 2. Which we can also simplify to x is equal to plus or minus 5 square root of 2 over 2. Next, we need to check if x, or what we just found, are in the domain of the original function. So now we have to take this original equation right here and put what we found for x in for that equation. So let's move over here. So we have our original equation, which is 300 minus 24 x squared over all of this. And now we want to put what we just got right over here in for our x. both of our x's. So we're going to take 25 minus x squared is equal or greater than greater than or equal to 0. Sorry. So for x to be positive, 5 square root of 2 over 2, and we're going to put it into this part right here. So then we have 25 minus 5 square root of 2 over 2 squared. So then we're doing the basic maneuvers of algebra. And then that's going to be equal to 25 over 2, and that is greater than or equal to 0, so that is true. So now, since we did the first, we're in the positive, we need to do the negative. So for x to equal negative 5 square root of 2 over 2, we will have 25 minus negative 5 square root of 2 over 2 squared. And because it's squared, this is actually going to turn into a positive, so it's going to be the same answer that we got from above, actually. So it's still going to be true. So both of these points are valid and are in the domain. And so we are nearing the end, knowing that from the beginning, a is equal to 4x of y, and 4x times the 3, 1x squared over 25, sorry. Knowing this equation here, we can actually plug in our x that we just found. And for y equals 3 times 1. So then we have minus 5 square root of 2 over 2 over 25. Don't forget the square. Okay. So then we're going to do the basic maneuvers of algebra again. 3 square root 1 minus 25 over 2 over 25. So then that can simplify to 3 times 1 minus 1/2, which can simplify even more to y equals 3 square root of 2 over 2. So our x equals 5 square root of 2 over 2, and our y equals 3 square root of 2 over 2. The length of the rectangle is 2 times the width, and y are and so is the y. So it's 2 times the y and 2 times x. So the dimensions of the inscribed rectangle of the maximum area is 2 times, and y is the same way. So what we just got for our x and for our y is what we're going to plug in for our x and y. So we have 5 square root of 2 over 2, and y equals 2 times 3 square root of 2 over 2. So then the basic math of that is going to be 5 square root of 2, and this would be 3 square root of 2. So our max area length is equal to 5 square root of 2, and our width is equal to 3 square root of 2. And that will answer all 3 parts of that very difficult question. If you have any questions, don't be afraid to ask. Thank you.